Okay, let me start now. Good evening, everyone. Welcome to the 13th lecture of the structure series of lectures related to structural engineering in this series of webinars conducted by the International Code Council, ICC. Today's topic is steel structures. So there will be two lectures. Today I'm going to give a lecture, and tomorrow again I'll give another lecture on steel structure. So today is steel structure 1. So far, most of the lectures that have been given were on basically on concrete structures. So probably this is the first lecture that is going to deal with structural material other than concrete, and in future we'll have masonry too. So we'll discuss whatever there is in Bangladesh National Building Code 2020, BNBC 2020. Now, steel structure, the chapter on steel structure is the chapter 10 of part 6 of BNBC 2020. Actually, in the previous version of BNBC, in BNBC 2006, steel structure was also in chapter 10 of part 6. So there is no change in chapter number. So this is kind of a self-sufficient chapter. So we don't have to refer too much to other chapters to design with steel according to BNBC. Only chapter 2 of part 6, which deals with loading, we have to calculate load based on that chapter, and chapter 5 and part 5, which is materials. There mentions of standards related to steel. But basically, chapter 10 is a self-contained chapter, and this is the longest chapter in the entire Bangladesh National Building Code. This one is the longest. So you can understand that this is a huge topic, and this is absolutely impossible to touch upon all the issues related to structural design of steel structures just only in 2 lectures. So we'll be selective. And secondly, the way I will discuss about different issues of steel structures will not be the way we cover the steel structure design in classrooms. We start with basic mechanics and we derive all the equations. My lecture on BNBC in this series will not be like that. We'll just refer to the equations of BNBC and the basic concepts. So, as I've mentioned that in BNBC 2006, steel structure design was there in chapter 10 of part 6, but at that time the chapter was based on AISC specification on structural steel buildings, allowable stress design and plastics design 1989, and supplement number 1 to the specification, which was the LRFD part of the design manual. So that was also in 1989, but LRFD was actually introduced in 1986 for 1986. So in 2006, that was quite updated from the perspective of that time. Now in BNBC 2020, it was written in 2009-10. So AISC 360.05 was actually followed, along with AISC manual 13th edition and many other publications of AISC, including publications related to hollow structural sections and publications related to seismic provisions. Now I'll just compare what is there in BNBC 2020 and what was contained in BNBC 2006. So if we go article by section, then we'll see that first three sections, scope, definition, notation, material are all included in the first section of BNBC 2020. Types of construction is also included in second section of BNBC 2020. Frames and other structures, these issues are mentioned in third section. Design requirements now are included in the second section, general design requirements. Now this one, working stress design, I've shown in red color. This one is omitted, but you know that in AISC 360 there is mention of ASD, allowable strength design, and this one was working stress design. These two are not similar, they are different, completely different. Working stress design method that was there in BNBC 2006 based on the earlier versions of AISC is completely different from the ASD, allowable strength design of AISC. We'll talk about that, but this working stress design method is now obsolete, so it has been dropped. Now load factor design method is included in actually in many different sections, all are related to LRFD. And connections, joints and fasteners, there is a section on connections. Serviceability requirements is one section on design for serviceability. Fabrication, erection and quality control, this is also a separate section. Surface treatment, I admit that this one was not entirely covered in the new BNBC. In the fabrication, erection and quality control, there is mention about surface coating, but not in the same way as it was in BNBC 2006. Design documents and other relevant design drawings and documents and the requirements of the design documents are mentioned in the first section of BNBC 2020. So all the 13 sections of BNBC 2006 except one, the 7th section on working stress design method, except that one, all other sections have been included in BNBC 2020 in different sections. But at the same time, many new sections have been introduced in BNBC 2020, like evaluation of existing structures, design of HSS and box member connections, direct analysis method, inelastic analysis and design, design for ponding, design for fatigue, structural design for fire conditions, stability bracing for columns and beams, and the last but not the least, seismic provisions for structural steel buildings. So you can understand just from the title of the section, you understand how important these new sections are. But these sections were not there in BNBC 2006. Now let's start the main topic. Now I understand just before starting this lecture, I found that in the question answer box there are questions already for me, and all these questions I found were related to seismic provisions, which we will cover in tomorrow's lecture. But even in at the very onset of this chapter, in the very beginning of this chapter, the code itself talks about seismic provisions. Now, it is said that the seismic provisions, which is the last section of chapter 10, we have to comply with that if the R value, that is response reduction factor in seismic loading, if the R value is considered more than 3, that is, we reduce the load for considering the inelastic capacity of the structure. If we use the R value more than 3, which is being called high seismic application, if we consider that, only in that case we have to comply with the provisions of section 1020, seismic provisions. Otherwise, we don't need to. Now, what does that mean? Let's see, when we use a value of R less than 3. I have mentioned here all the building types which are related to steel structures. And if you see the second column, R, you'll find that all the values are more than 3 except one, the last one. So, and the last one is related to, which is G, steel systems not specifically detailed for seismic resistance. Only for those structures we can use a value of R less than 3. Even for ordinary steel moment frames, the value of R is 3.5. Ordinary steel concentrically braced frames, the value of R is 3.25, which are more than 3. And even for the ordinary moment frames or braced frames, we'll have to comply with section 1020, that is seismic provisions. We'll discuss about that tomorrow, how much of that are related to ordinary moment frames and how much we have to follow for special moment frames. That we'll discuss tomorrow. But as of now, you can understand, even to design an ordinary steel moment frames, we have to comply with section 1020, which are seismic provisions. If we intentionally go for systems which are less ductile, and if we intentionally increase the force for which we want the structure to behave elastically, in that case, those structures will be not detailed for seismic resistance, and we can assume value of R less than 3 or 3. And in that case, we are free not to comply with the seismic provisions section 1020. But in case of seismic design category D, you remember that for zone 4, we have to design the structures complying seismic design category D. In that case, we are not permitted to design steel systems not detailed for seismic resistance. That we are not permitted to. This is NP, not permitted. Okay, so even for zone 4, zone 3, seismic zone 3 of Bangladesh, if the soil is not rock-like, if even for stiff soil, we have to design structures complying SDCD. And for seismic zone 2, if the soil condition is not good, if it is not firm or stiff, then we have to design the structure complying SDCD. But if we can design structures for SDCC for seismic zone 1 and 2, and in very special cases in seismic zone 3, in that case, or if we design structures according to seismic design category B, which is basically only in seismic zone we can do that, zone 1 we can do that. In those cases, we can design structural systems, steel structural systems, not detailed for seismic resistance. Okay, so this is very important information, and the chapter begins with this almost. Now next comes material for different types of steel sections, like hot roll sections or cold form sections, or built-up sections, or castings, forgings. All the standards that are mentioned in this chapter are either ASTM standards or BDS standards. There is no mention of any other standard, and interestingly, no other standards are basically allowed. Only ASTM and BDS standards are allowed. So this is a very, very important piece of information, because in Bangladesh we import steel sections from many different countries, and many of those countries do not follow ASTM or BDS. They have their own standards. But in Bangladesh, if we want to design steel structure, we must follow material standards ASTM and BDS. So what is the choice? The choice is wherever the place we import the steel sections from, but those sections must pass through all the tests mentioned in ASTM. So that is a must. So although in the material chapter, material part, this is part 5, there are mentions of other standards related to steel, but in chapter 10, for design purposes, only ASTM and BDS standards are mentioned. So this is very important. AISI is mentioned there, that is AISI basically related to ASTM. So American Iron and Steel Institute, AISI, and AWS is also relevant for welding, American Welding Society. But other than that, no other standards are mentioned in chapter 10. So I've already mentioned about the design basis, that LRFD is the standard design basis now, which is load and resistance factor design, which is the ultimate limit state is considered in this case, although we design for serviceability too, but all the basic checks are in the ultimate limit state. So this is load and resistance factor design. Now there is another design method that is also allowed, is allowable strength design. Be careful, the term, not stress. In ASD, the term is allowable strength design. But previously in BNBC 2006, what we had was working stress design method. These are two different things. Now, what is the difference between LRFD and ASD? Basically, if we want to, we can follow either one. We have to do almost similar calculations. Like the basic term for capacity, which is nominal strength, the nominal capacity, Rn, we have to calculate Rn whether we design according to LRFD or ASD. Rn is the common term. We have to calculate the capacity, nominal strength in the for ultimate case. That we have to do. And then for LRFD design, we multiply it with the resistance factor, with a reduction factor, kind of capacity reduction factor, resistance factor. And then we compare with the required strength, that is the strength needed from the point of view of load. Now, in the calculation of load in the LRFD method, we use another factor, which is load factor. So we increase the load, assuming the uncertainty of the loading in the extreme cases, ultimate limit state. So we increase the load and we calculate capacity, the inelastic capacity, and assuming the uncertainty of the material properties, we reduce it. So that is LRFD. What we do for ASD is that we calculate the capacity nominal strength for the ultimate case. That is the inelastic capacity. Then we use a factor, a safety factor. This is not factor of safety, this is safety factor. And we divide by that, we reduce it by a larger margin so that we can compare the strength or capacity with service level demand. That is, RA is the required strength for allowable strength design. Now, for RA, we follow the service level loads. We don't increase the load with an overload factor. So you can assume omega as a combination, safety factor as a combination of overload factor and safety factor, something like that. So the calculation in terms of the calculation steps, there is not much difference between LRFD and ASD now. So basically we have to calculate the nominal strength. But previously in working stress design method, and the capacity that was calculated for working stress design method was a working stress capacity. That is not the ultimate level nominal strength capacity. So the very derivation of the capacity was very much different in the earlier case. So this is the design basis. We can follow either LRFD or ASD. So in terms of the steps of calculations, these are quite similar. Now, load combinations. This is interesting. In previous code, version of our code in BNBC 2006, there were separate sets of load combinations for concrete and steel. We had two separate sets of load combinations, both for working stress and ultimate strength design, and working stress design. We had two different sets of load combinations for steel and concrete. In BNBC 2020, we don't have that. We have both for concrete and steel. For strength design, we have a set of load combinations, and for allowable strength design, we have a different set of load combinations, but these are same for concrete and steel. So this is very important. And since you have already covered the concrete part, so you are familiar with the load combinations. Now, so far we have talked about when we should consider the seismic provisions. Then we talked about the design basis. Now, for steel structure, this is very important. Connections. Connections are very, very important for steel structures. So this one is also, we'll cover the provisions related to connections tomorrow, in tomorrow's lecture, but the types of connections are mentioned in the very beginning of this chapter. So connections are classified in two types: simple connection and moment connection. So previously in BNBC 2006, the terms were rigid connection. Instead of moment connection, it was called rigid connection and simple connection. So now we call it simple connection and moment connection, number one. And second, Moment connections are then classified into two different types: fully restrained connection, FR, and partially restrained moment connections, peer connections. So there, the previous terminology that were used in BNBC 2006 were rigid connection and semi-rigid connection, is semi-rigid connection and rigid connections. Now the terms are different: fully restrained and partially restrained. Now you see that BNBC 2006 was based on AIC 1989, AIC 360 1989, and BNBC 2020 is based on AIC 360 2005. In between, there was a time when AISC used to classify connections in three types: simple, fully restrained, and partially restrained, like that. And in BNBC 2006, it was probably simple, rigid, and semi-rigid. But now there are two types of connections: simple connection, moment connection, and moment connections are then classified into two types: fully restrained and partially restrained. So simple connection, though the term is simple, the calculation may seem simple, but there is a big important thing that we shouldn't overlook, is that in simple connections, the connections do not transfer moment from one member to another, that is from beam to column or column to beam. It doesn't transfer the moment, it transfers only the shear force. However, since it doesn't transfer the moment, due to the member and moment, the connection itself goes under rotation. And like we have to be sure that the simple connections have sufficient rotation capacity. And inelastic rotation is also permitted in case of simple connection. So there will be relative deformation, relative rotation between beams and columns. In case of fully restrained connections, that rotation is not allowed. So it has to have enough rigidity so that it can transfer the full amount of moment from beam to column or from column to beam. So that rigidity must be ensured. And in case of partially restrained connections, the connection details are such that they can partially transfer the moment from one member to another, but at the same time, they have some amount of relative rotation between beams and columns. So the connection itself goes under some rotation, and at the same time, it also transfers some amount of moment. So in this case, we have to ensure that the amount of moment that they're supposed to transfer, if they have the rigidity for that, and the relative rotational capacity should also be ensured. In this case, the moment curvature relation, if we plot the moment curvature relation, that gives a non-linearity into the system. So if we use partially restrained connection, and if we want to take that into account in our analysis, in that case, we have to go for nonlinear analysis. Remember, nonlinear analysis doesn't mean inelastic analysis all the time. Yes, inelastic analysis itself is nonlinear analysis, but nonlinearity can be induced many different ways. Partially restrained moment connections are one such way that which makes our analysis method nonlinear without the materials going into inelastic phase. So there are issues related to analysis if we want to use partially restrained moment connections. Now, if we see some figures, for our understanding. So I'm pretty sure that most of you are very much well aware of simple connections and effort connections. Simple connections, they don't transfer moment. So what happens if we want to transfer moment? Flexural stresses are where the flexural stresses are more and where the flexural stresses are less. The flexural stresses are maximum at the extreme fibers, right? And they're nil at neutral axis. So in case of an I section, the section that is shown here as a beam for simple connection. So this is an I section. The moments above the strong axis, the moments produce maximum stresses along the flanges, right, of this I section of the beam. So the flanges should be rigidly attached to the columns. Beam flanges, I sections, the flanges of the I section of the beam should be rigidly attached to the columns if we want to transfer the flexural stresses. But in case of simple connection, these flanges are not attached to the column flange. Only the connectivity is provided through web of the beam. You see, for the beam is connected by its web. The web, in the web, we know that shear stresses are maximum in the web. So when the beam is connected to the web, shear stresses are transferred, but the flexural stresses are not transferred since the flanges are not connected with the column. So that is a simple connection, and this is called simple shear connection too. In case of effort connection, so the connection, they are connected both at the web and at the flange. In fact, the flanges are welded with the column flanges. The beam flanges are welded to the column flanges and made rigid. And you see there are stiffeners along that line. So this is a typical detailing of fully restrained connection. So all the flexural stresses that are produced due to moment in the flanges, those are transferred to the column. In case of partially restrained connection, we'll also discuss about these things tomorrow, but here to give you some idea, in case of peer connection, you see from the first look, they look very similar to the effort connection, fully restrained connection, but the difference is that the flanges of the beam are not welded to the column flanges. Okay, so when the moment comes, the flange stresses are somewhat transferred through the angle that is connecting the beam flange and the column flange. But these angles, they undergo some deformation. When they undergo some deformation, there is relative rotation that is produced, that is shown here as theta. Relative rotation is produced between beam and column. They are no more rigid. When the angles connecting the beam flange and column flange, they themselves undergo some deformation, then there is relative rotation between beams and columns. And that makes the connection partially restrained because full moment is not transferred. Some amount of relative rotation is induced in this case. So these are basic definitions of the different connection types. Another important classification that we have to understand at the very beginning of the structure design are unstiffened and stiffened elements, not members. We are not talking about stiffeners. This is not related to stiffeners. Although we are using the term stiffening, but here it has some different meaning. We are talking about elements of members. Like flange is an element of an I section, or web as an element of a T section, for example, like that. So we are talking about elements of sections. So in the same section, there might be some elements that are stiffened and some elements that are unstiffened. Now, what's the definition of stiffened element and what's the definition of unstiffened element? Unstiffened element is being defined as the elements that are supported along only one edge parallel to the direction of the compression force. So think about of an I section as a beam and think of the moment that is coming onto it. Think about the compressive stresses on one flange of the I section and the direction of the force. Now, in parallel to that direction, along that direction, the flange of the I section, one flange, in how many edges that is connected in the member. We'll show some figures, then it will be more clear to you. So a flange is connected to only one edge parallel to the direction of compression force. So a flange in an I section is basically for moment about strong axis is unstiffened element. But in case of a web in an I section, the web is connected in two edges, one at the top flange with the top flange and one with the bottom flange. So a web in case of flexure above the strong axis is a stiffened element, as a web is supported in two edges. Now, why we need these definitions of stiffened and unstiffened element? Remember, in steel design, the most important thing is buckling. We have to always be very, very concerned about this phenomenon, which is called buckling. So in steel design, we always have to think about buckling. What is buckling? You know that since steel is a very strong material as compared to other materials like concrete or aluminum or other materials, steel is a very strong material. That's why we need very thin sections of steel to carry loads. Now, when the sections are thin and the members are long, in case of a very thin and long sections, so they become slender, right? L by R ratio, you all know, slenderness ratio. So steel sections tend to be slender, and whenever compression is induced in whatever forms, that tends to make the steel sections buckle. So that is why buckling, we have to always be very, very careful about buckling. Now, there are different types of buckling, you know, I'm sure that you know that. One is the beam buckling, that is a column buckling, that the whole column buckles, right? In your engineering course in the second year, in level 2, you have, I'm sure all of you have in your SM lab tested long slender columns, we call them columns, and we applied compression and they were buckled, and we calculated the critical buckling load. I'm sure about that all of you have done those tests. So now we know about column buckling, that the whole column may buckle. But in steel sections, there are problem that this local buckling is another very big problem, that the whole section may not buckle. The whole section may be quite stocky for the load that is coming onto it. For example, a column, the column itself may be very short so that it doesn't buckle, but due to maybe due to bending, or maybe due to even shear, maybe due to even torsion, maybe due to a point load on the structure, an element of the member, like a flange or the web of the member, may buckle. So if probably the whole section of a column may be strong, but the flange or the web may be too thin. Perhaps, suppose we have very thick flanges, but the web is very thin. In that case, we may experience that the column, the whole column doesn't buckle, but the web buckles, like the web buckling. We don't have figure here, but these are flange buckling. It may happen so, or the flange at one place or some places they may buckle. There are some pictures here. You see the whole, say, in the top most picture, you see the web is straight, so the whole section didn't buckle, but the flanges buckled in one place. In the bottom picture, in the right hand side or left hand side, the column is straight, upright, but some elements buckled. So we have to be very careful about that. So that's why we need to know which elements are stiffened and which are unstiffened. Why we need to know that? Because we want to define slenderness ratio for the elements. We have slenderness ratio defined by length of the member divided by radius of gyration of the member, L by R ratio. We know that. But we want to define slenderness ratio for the flange, not the whole section. We want to define slenderness ratio for the web, not the whole section. In that case, how we can define that? In that case, this definition of stiffened and unstiffened element is very important. In case of unstiffened element, like the flange here, in this table of BNBC, it is shown which the B by T ratio, for example, is the slenderness ratio, and how to define B and what is T. These are shown in pictures like these. And depending on these B by T ratio, and in case of web, H by T ratio, TW is the web thickness, H by TW ratio, we define the slenderness of the elements. And we check if a section is susceptible to local buckling or not. And by checking that, we put some limits on these slenderness ratios. And comparing, these limits are shown here, lambda P, lambda R. What they mean, I'll explain in a short while. So these are some limits. Based on these limits, and we compare the B by 2T or H by TW, the slenderness ratios with these limits, and we term a section compact or non-compact. That is, the section is susceptible to local buckling or not. Basically, that is the information we get from these definitions. We'll say them. Now, one thing I want to mention that in this table, both unstiffened elements and stiffened elements are tabulated. But there is a mistake in BNBC 2020. The mistake is that there is no line dividing these two types of elements in BNBC 2020. Actually, in this slide, you see the first one is 9, number is 9, and there should have been the top margin of this cell should have been continued at the very left cell. So there, that would demarcate stiffened elements from the unstiffened elements. So in this table, items 1 to 8 are actually unstiffened elements, and item numbers 9 to the rest of the elements are stiffened elements. So this is a mistake in BNBC 2020. So this line, the top margin of cell 9 should have been continued all through. So I hope you'll remember this, and that will not cause any problem for you. But this is obvious. You can understand which one is stiffened and which one is not stiffened. For example, this web of item number 9, the web itself is supported in by the two flanges on two edges. So this is stiffened. But in item number 1, the flange, it is supported only along the edge with the web. So supported only in one edge. So this is unstiffened element. So this is obvious. This shouldn't be cause any big problem for you. Now let's talk about what is the meaning of lambda P and lambda R. Why we need to define compact and non-compact section. So many terminologies. We'll be familiar with them very soon. By compact section, we actually predict that how these sections will fail. When they will fail, how they will fail. And non-compact sections, how they will fail. And we are bringing on another term, slender elements. Slender element section. So that a section that has some slender elements in it. Now, first, how to recognize them. Second, what do they actually mean? I'm saying that they mean how they will fail. So let's talk about that. First of all, let's see that there are two types of limits. One is lambda P and another is lambda R. We'll compare these slenderness ratios with thickness ratios, V by T or H by TW, whatever is written, and how they're defined is shown here. We'll compare with lambda P and lambda R. Now it is very easy. Now, if these slenderness ratios with thickness ratios are less than lambda P, then we call them compact section. If these ratios are greater than lambda P, but less than lambda R, we call them non-compact section. If these ratios are greater than lambda R, obviously greater than lambda P is always much smaller than lambda R. So if they are greater than even lambda R, then we call them slender element section. The section we define the section like this. Now, what does it mean? From analysis of the way these limits are derived, we can say that these sections, for example, compact sections, when they will fail, they will fail by yielding, not by local buckling. That is, since the weight thickness ratio, which is like slenderness ratio, is so small that they're stocky, kind of stocky column. So they're very stocky. They don't tend to buckle. So yielding they will experience yielding, that sigma y, that is yielding stress will reach much before the critical Euler buckling stress will reach. So they will first yield, and not only that, the whole section will yield first before it buckles. So that is compact section. Non-compact section, that is the whole section will not yield first, but some part of the section will experience yielding. So in these types of section, there will be some areas, some locations where there will be yielding, where the fiber stresses will go beyond or will reach sigma y, yield stress. But there are, even after it becomes inelastic, they will tend to buckle. So they will experience inelastic buckling. They will buckle. They will not be completely yielded, but there will be some portions in the section which will yield. So it will go into the inelastic zone. But in the inelastic zone, it will buckle. Slender sections are that they will experience elastic buckling. That is, they will experience local. There will be no yielding in anywhere of the section. So they will, there will no yielding anywhere of the section. There will be local buckling. So this is all about local buckling. Remember, similar situation will be there for even for the beam buckling case too. There will be 3 stages, and this is related to sections, elements, and local buckling. So based on local buckling criteria, we define sections in 3 types: compact section, non-compact section, and slender element section. Most of the time we try to make our sections compact because we don't want to take the risk of local buckling. But we can design for non-compact section too. But slender element sections are always advisable to avoid. Although there are criteria for that, but that will make the sections inefficient. But we can design that. So you see, as I have already mentioned, for steel design, buckling is a major problem, and we have to always be careful about that. So buckling analysis is called stability analysis. So when something buckles, we call them instability. So stability design is very important, particularly for lateral load. This is very important. Gravity loads will impose compression on columns, but at the same time, when there is lateral load, and that causes some problem. We'll see that. So stability design requirements. For stability design, we have to consider 4 things which causes instability. One is second order effects. We'll discuss about that. Second order effects. Second is flexure, shear, and axial deformation. Naturally, we know that flexure causes compressive stresses, and in steel, compressive stresses causes buckling. Shear doesn't cause normal stress, no compressive stress apparently. So how can it cause buckling? It causes buckling. We'll see that, how shear causes buckling. Axial deformation, similarly, axial deformation, compression definitely will cause buckling. Now, geometric imperfections, I think many of us are quite aware of these things. The geometric information, for example, a column may not be straight all through. There might be some geometric imperfections, or the flange or web that may not be completely straight. We teach these things in third year, level 3, and fourth year. I'm sure that you have also read about this, studied about this in some way, yeah. But they cause, if we want to consider these geometric imperfections, we have to go for nonlinear analysis. So, and they also cause, they also hasten the buckling. So geometric imperfections are important. We'll discuss a little bit about that in direct analysis method, DM, which I'm trying to cover tomorrow. So today we'll cover the basic things. Basically, I think even to cover basic things, it will take a long time. You understand that this steel design is undergraduate. We have an undergraduate course. We have graduate courses on that, and even with those graduate courses, we cannot completely cover all the aspects of steel design. And If you follow AISA, you will see that there are so many publications, manuals, and so many training materials. So you can understand this is a vast, vast subject. We'll just scratch on the surface of this one. So you kind of get introduction to this, and you have to do a lot of self-study to master structural design of steel structures. Now, member stiffness reduction due to residual stress. I'm also sure that you know about residual stress. For example, if we apply you have covered it in the second year, level 2 in SM, solid mechanics. If we apply bending on a member, and then if we unload the bending and reverse the bending in the opposite direction, that causes residual stresses. You did a lot of problems on that too. But these residual stresses, when there are already compressive stresses in the structure, but here the way the residual stresses are introduced in the member is different. I'll talk about that. But once there are residual stresses, already some compressive stresses in the structure, then it reduces the capacity to allow for more compressive stresses. It will buckle earlier. So these are the 4 things that are very important from the stability point of view. So in any design, we have to consider these 4 effects. Now, let's talk about secondary effects. What do you understand by second order effects? We have the same things even for concrete, but still, since concrete sections are not slender, so we don't have to bother about them all the time. But if we go for nonlinear analysis like pushover analysis, then we have to consider these effects, some of these effects. But in steel, we have to consider these effects. These are important. What are these second order effects? Now, this is very simple. Suppose this is a simply supported beam. It is subjected to a concentrated load at the mid span F. Then it deflects by an amount of delta, small delta 1. Then suppose it is subjected to an axial force P. So if we calculate moment without considering the deflected shape, if we consider only the undeformed shape, the straight line of the beam, the skeleton of the beam, in that case, we'll calculate the maximum moment to be PL by 4, FL by 4 in this case. F is the transverse load, FL by 4. But if we consider the deformed shape, and if we see that due to the application of F, there is deflection delta, this P load at the left side, the axial force, this P load will introduce an additional amount of moment in the mid span, which will be P delta 1. So the delta, you know that for calculation of deflection, what we need moment diagram, right? From moment diagram using unit load method or virtual work method or elastic load method or direct integration method, whatever method you follow, if we want to calculate deformation, then we need the bending moment. So with the FL by 4 bending moment, maximum bending moment at the mid span, if we calculate, then we'll get delta 1. But that the P load causes an additional moment. So if we calculate deformation again, we'll see that no, delta 1 is not the final deflection. Due to the application of P delta 1 moment, it will deflect more. And suppose the final deflection is small delta. So then actually the moment in the mid-span now is FL by 4 due to the F load and P into small delta due to the axial force. This P small delta, this is a second this is called secondary moment. So this is this is called P delta effect. Now, to consider this, we cannot apply equilibrium condition on undeformed shape. We have to consider the deflected shape, and then if we apply equilibrium condition, only then we can consider this P delta effect, P small delta effect, or secondary moment, effect of the secondary moment. So that causes our analysis to be non-linear. In a linear analysis, where we apply superposition theorem, we cannot deal with this thing. So this causes our analysis to be non-linear. So first second order effect is this, we call it P small delta effect. Another one is in the global level. This is individual members, and the secondary moment due to the bending of individual members is called P small delta effect, second order effect. But in the global level for the whole structure, for example, the one I'm showing it at the bottom of the page, this is brace frame, whatever. So due to the lateral load, the red F at the right side, there is a sway. There is a drift or sway of the frame. And if there are vertical loads, gravity loads, say P on the top, blue P, that causes an additional moment. This, say the drift is delta, capital delta. So that causes another moment at the bottom, which will be P capital delta. If we don't consider this sway in calculating the moments, if we calculate moment in the undeformed shape, then the moment will be this F into the height of the frame, FH. But after the deformation, this capital delta, if we calculate the moment at the bottom, that will be like FH plus P capital delta, P big delta or large delta. Different people term it in different ways. So P large delta. So this is another effect. This is not in the individual member level. This is in the global structural level. So there are two P delta effects, second order effects. One is in the global structure level, which is called P large delta effect. And another is due to the bending of individual members, which is called P small delta effect. Now, usually both happens together. So in case of a column, see, the column experiences due to lateral load, sway or drift, large delta, and then due to vertical or gravity load, it also bends, and that bending causes another additional deformation, small delta, P delta. So if we think about moment, then let's start from the right side. Due to the H horizontal load, we get H into the, if the length of the column is L, H into L as the moment, if we calculate moment on the undeformed shape. But due to that lateral load, it will experience a drift of this delta, large delta. So that for vertical P load, gravity load, this will experience another additional moment P large delta. Due to application of these moments, and at the same time the vertical load and lateral load, the column as a member itself will bend, and that bending will cause a small delta moment that will not be at the bottom, that will be maximum in the mid span of the member. So the shape will be something like this one. You see the third sketch on the right side. So if we superpose all these, then we get the maximum moment. At the bottom, the moment will be like HL plus P large delta, but in the middle, it will not be just the summation of the right two moments at the right hand side. There will be another small p small delta moment here. So this is the ultimate second order effects. If we consider both p large delta and p small delta effects. So these are the second order effects. We have to consider both. Now we'll discuss a little bit more about these things, how these things can be considered in our analysis and in the design too. Now you remember we talked about, we say that 4 things cause buckling, or what did I say? Sorry. Stability design requirements. One is second order, another is flexural shear and axial deformations that we'll see, and geometric imperfections. It's very difficult to consider them analytically, but there are ways. We'll talk about that tomorrow in the direct analysis method. But we have to consider the member stiffness reduction due to residual stress, and now how they are induced in a member, in steel member. Residual stresses are stresses that remain in a member after it has been deformed into a finished product. In case of steel, we term residual stresses, we define residual stresses like this. That is, after production of the section, the member, the stresses that are inbuilt within the member, or during production, just after production. The members may be finished product from a factory. The member may be produced at a site. Whatever be the case, in the finished product, if we have stresses within the member, if there are trapped stresses, we call them residual stresses. Now, what are the sources of these residual stresses? The most important source is the first one, uneven cooling. Because to produce steel sections, we have to heat it up and then roll it, or cold form it, or we have to join 2 plates by welding, and that causes the temperature at the joint to rise. Then the section cools down, but the cooling does not happen evenly over the whole section. It is at some locations the cooling happens faster, at some other locations the cooling happens slower. And you can understand, for example, if you have something in your hand and suppose some part is cooling down very fast and some part is cooling down very slow, you can, I think you can feel that there will be stresses, because at some location it will try to contract, at some other location it will try to expand, and that will cause stresses internally. So that is the source of residual stresses, uneven cooling. Second is fold bending and cambering during fabrication. So once we bend something and keep it like that, that causes stresses to be trapped inside in those locations. Punching of holes and cutting operations during fabrication, you understand? When we punch a hole, just by the side of those holes, there the material is no more elastic, because when you cut out material from that side, just adjacent to the cutting surface, the material becomes inelastic. So that means the level of strain is much higher than yield strain. So that causes stress inside the material. And as I said, welding, which is similar to uneven cooling. Now, if we see the picture at the right side, there is shown some places there residual stresses, compressive residual stresses, and at some places tensile residual stresses. Why is that? Why is it like this? At the flanges, at the outer edges, there will be compressive stresses, and in the flanges with the junction of the wedge, there will be tensile stresses. In case of web, in the middle, there will be compressive stresses, and at the joint with the flange, there will be tensile stresses. Why is it like that? This because the free edges, like the sides of the flanges, or in the middle of the web, these locations get cools down faster, and near the junctions, the joints with, between web and flange, it cools slower. So that causes these residual stresses like this. So if we see on the right side, once it starts cooling down, the outer edges of the flanges, they cool faster, and that causes some compressive stresses to be there. And then the middle of the web starts cooling down, that causes some compressive stresses in the middle of the web, and gradually the whole thing cools down. But in this process, there are compressive stresses at the edges of the flanges and the middle of the web, and in other places there are tensile stresses. And due to these residual stresses, when actual load comes onto these sections, then the additional compressive stress that causes local buckling. Now, if we want to consider all these effects, these second order effects, the effects of residual stresses, and geometric imperfections, and what else, and normal flexure shear axial forces, if we want to really consider all these in an exact way, then we have no other choice but to consider inelasticity and go for nonlinear analysis. So, but usually in the design office, we don't want to go for non-linear inelastic analysis because they're very, very time consuming. The modeling of part of this is difficult, and to run the program, it takes a lot of time. So we want to avoid this too theoretical type of job, right, in the design offices. So you always prefer elastic analysis. So actually our code allows us to, for elastic analysis, then what about all these effects that we have been talking about? The code allows us to consider those effects in an indirect way if we want to go for elastic analysis. So analysis method, there are two types of analysis methods, elastic analysis and inelastic analysis. In the elastic analysis, there is a traditional effective length method that is usually for buckling. We always go for slenderness ratio, L by R, if you remember that KL by R, say effective length factor. Depending on the support condition, we modify the length and we call it effective length. So that approach is there. So in elastic analysis, we can go for that approach, KL by R, effective length method. And there is a new method that was introduced during that time in 2005. So this is a very new method, and very recently, probably in 2016, this is the primary method in AISC. Now, direct analysis method is the main method now. Previously, it was kind of a secondary method, an advanced method. Now, if we follow AISC, not in BNBC, in AISC, this is the primary method. We are supposed to follow direct analysis method If somebody wants to follow effective length method, still this is allowed, but direct analysis method is the recommended method. Now, in direct analysis method, although still this is an elastic analysis method, but this is much more sophisticated compared to effective length method. We can consider all those 4 aspects of stability in the direct analysis method. In effective length method, everything is approximate indirect way. So in effective length method, there are 2 types of analysis. First order analysis, that is usually the analysis we prefer, that is elastic, completely elastic, without any kind of inelasticity and without the consideration of p delta effects, etc., etc. The normal like stiffness method type of finite element method, but like stiffness method where superposition is valid. That type of analysis is first order analysis. And another is second order analysis, that we modify the first order results and consider the second order effects. That's second order analysis. So usually we try to go for first order analysis, but there are limitations. So the code imposes restrictions that when we can go for first order analysis and when it is not valid. So the situations when that is not valid, we have to go for second order analysis. So far, that is the usual practice. Either go for first order analysis, if that is not permitted, then go for second order analysis, and that's it. But recently, as I've said, that AISC recommends direct analysis method for stability analysis. So tomorrow, hopefully, I'll touch that to direct analysis method. It's already 9 or 8. I'm so sorry. I have a lot to cover and I'm going too slow. I'm extremely sorry. So now, first order analysis. And first order analysis, these are the conditions. This is the first one, is that if the strength is so high, the required strength, that is the demand, is much smaller to the actual capacity of the section, then of the all the sections, then we can go for first order analysis. That is, if the required strength alpha PR, where alpha is for LRFD is just 1, and for ASD we increase the required strength, right? So 1.6. So if alpha PR, the required strength, is less than the 50% of the yield strength, so in that case we can go for first order analysis. Secondly, we have to provide additional lateral load at each story level in both X direction and Y direction independently, not at the same time. Once in the X direction and in another load case in the Y direction. So this additional load, lateral load in I, it is first we have to run the problem without this additional load, and we have to calculate the deflection, first order deflection. Then from the story drift, delta by L drift ratio, if we multiply the gravity load with this story drift ratio and 2.1, so about twice the amount of the story drift ratio, then the amount of load we will calculate, that we'll have to apply again at each story level. This is an indirect way of considering some of the second order effects. So, and yeah, at least we have to apply 0.0024 of gravity load at that level. Then another thing is that P small delta effect must be considered. Non-sway amplification B1, which is related to P small delta, that is individual member bending effect. Non-sway amplification of beam column moments is consider. That we have to consider. So we'll do first order analysis. We'll calculate the storage drifts. Then we'll, from those storage drifts, we'll calculate the NI, lateral load, additional lateral load at each story level. And we'll also, in the design, we will also have to consider the end moments, and we have to amplify the stresses, considering the P small delta effect. So we are considering second order effects. The code compels us to do so in an indirect way. And after doing all these, we have to ensure that alpha PR is less than 50% of yield strength. In that case, we can go for first order analysis. Now, second order analysis. In second order analysis, what we do, we consider both the P small delta effect and P large delta effect indirectly. What we do, there is one analysis method suggested in AISC, which is called NTLT method. There is no translation and lateral translation method. For an example, let's suppose that we want to analyze the portal frame shown at the bottom left. And the portal frame is supposed to be subjected by a gravity load of a uniformly distributed load at the beam and a lateral load at the beam column joint, capital H, at the left. So it will have lateral load and gravity load, uniformly distributed gravity load. So normally what we are supposed to do, we are supposed to apply both the loads and calculate the bending moments, right? But by doing that, we are not considering P small delta P capital delta effect. What we can do is that what is recommended is that first we'll do a no translation analysis. Like we may suppose that there is no sway. We'll provide an artificial support at the left corner. Suppose there is a hinge there, and then we apply the vertical load only, and then we'll calculate all the moments. We'll term these moments and the axial forces MNT or PNT. No translation moment, no translation axial force. And then while doing that analysis, there will be a reaction in the support, this imaginary fictitious support, there will be a reaction. What we'll do, we'll apply that reaction force along with the original lateral load H. So H and this reaction will then apply together as lateral load, but this time there will be no vertical load. So we'll apply the lateral load, and then again we'll calculate the moments and axial forces. We'll call them MLT and PLT. Remember, the P large delta is related to sway only, and P small delta is related to basically member bending. So in an indirect way, these two terms are separated in this type of no translation, lateral translation method of analysis. So what we will do to calculate the moment of the members, we have to multiply one amplifier B1, which is related to P delta effect, with the MNT, no translation moments, and we'll amplify the lateral translation moments with another amplifier, this is P large delta amplifier. So in case of axial force, there will be only the effect of P large delta amplifier B2, not the P small delta amplifier P1. So now I'm not going into the detail, I'm just giving you the concept, how to consider the second order, how to do the second order analysis. This is the second order analysis. And from the code, you can easily find out the expressions for B1 and B2. So then you can calculate them. But this is the concept of taking into account second order analysis. Again, like the first order analysis, that is valid only in this case, that is alpha PR must be less or equal to 50% of PY. in case of second order analysis, there are restrictions, like after doing the second order analysis, the total sway, second order sway that we get, drift or sway, and from the first order analysis we'll get another sway. The ratio of these two must be less than 1.5 if we want to adopt second order analysis the way I have just mentioned, no translation, lateral translation method. If it is more than 1.5, then we have no choice but to abandon these simple methods, but to go for direct analysis method, which is a very recent method. I'll talk about that tomorrow. Now, so all the other things that I think quite straightforward, like even in the second order analysis, we have to consider minimum lateral of 0.002 yi. Yi is the gravity load at certain ith level. So we have to multiply 0.002 with gravity load and apply that as lateral load, even if we don't have any lateral load at any certain level. This is the minimum amount of lateral load that we have to apply. This is kind of notional lateral load that we'll talk about in direct analysis method later. So, and another thing is that we can assume K as 1 if the delta second order divided by delta first order is less than 1.1. If it is not so, then we have to go for a side sway buckling analysis, that is, depending on the end moments, what should be the effective length that we have to find out. And there are charts for that. We have to consider those charts. If delta second by delta first is more than 1.1, others we can conservatively take K as 1. Okay, K is 1, that means what? That means simply supported, right? But we know that there are rigidities, so K should be less than 1. But this is very conservative if we take K equal to 1. In many cases, we actually be very conservative. We take K as 1. Now, the things that I have covered, these are the basic things, basic concepts that are needed to start going for structural steel analysis and design. Now we'll talk about design. These are pretty straightforward things like textbook information. So if we consult any structural steel design textbook, you'll find all these formula. So you can look up those formulas from the books and do your design. I'll just cover them, but for purpose of completeness. And at the same time, I'll also try to give you some concepts for different modes of loading. For tension members, that is the members that are supposed to be subjected to only tension, like anything hanging from a rod or something like that, only tension members. So the members that are supposed to be tension members, still for those members, we have to design in such a way that slenderness ratio must be less than 300. Okay, so slenderness ratio can never be more than 300. Then we have to increase the size of the section. In the gross section, we have to compute, we have to give two checks. One is at the yield stress level check, that is the capacity we'll calculate is Fy into Ag. So for yielding, to check yielding, we'll consider the capacity by multiplying yield stress with gross section. In most of the cases, the pi values used for LRFD and omega value used for ASD are mentioned just with the formula in most of the cases in the code. So you'll have to be always careful about those factors. So for case of tension, phi is 0.9 and omega is 1.67. For yielding, check of yielding, for the tensile rupture check, that is the failure check. In that case, we will calculate the capacity to be Fu, that is ultimate strength, multiplied by an effective area. Now, what is the effective area? We'll see. So, not the gross area, effective area into ultimate strength. And in this case, the phi values and omega values are different. Now, effective area is shown as AN, that is net area multiplied by a factor shown as U. It is called shear lag factor. Why you need this factor? We'll see. Now, AN is in case of, for example, if two members are bolted together and one of the member acts as tension member, at the location of the bolting, there are holes, right? Now, if we subtract the areas of those holes, or the cross-sectional area of the holes, then we'll get the net area. There are rules for that, how much you have to subtract, etc. I'm not going into the detail in those, but we can calculate the net area, but we have to multiply with that one factor that's called shear lag factor. Why do we need shear lag factor? You see, for tensile members, we assume that we use Navier's hypothesis that for derivation of the formulas that is all the tensile stresses are uniformly distributed over the entire cross section. So that is the assumption. But for example, in the case shown above in the top, you see there is a picture of an angle welded on a plate. And you see the angle at the location of welding is at the bottom. In that case, if the angle is subjected to, at one end, subjected to tensile forces, the distribution of stress in the angle will not be uniform because the angle is connected with the plate at the bottom. So the level of stress will be higher because the stress will be transferred at that level, and at the top edge of the angle, there will be little stress because that is almost free. So even though usually for tensile cases, for the cases of tensile mode of loading as tension, we usually assume that the tensile stress is uniformly distributed across the section. That doesn't happen in all the time. So this effect, this is called shear lag effect. Because of the shear transfer at the bottom here, the tensile stresses at the cross section, that is no more uniform. There is a lag. This shear lag factor, there are formula for that, and for different types of sections we can calculate this shear lag factor U, and we can multiply this with net area and we'll get effective area. So for rupture, for the check of rupture, it's like tear, complete tear, we use this shear lag factor. For pin connected members, there are additional formula. Will not go into the detail. There may be two types of ruptures. For pin connected, there may be shear. That is suppose there are bolts along a line. So along that line, the member can shear out, can be completely sheared. So that is shear rupture. For tensile member, there may be tensile rupture, that is, it can tear off, or it can be cut along the line of the bolts, that is shear rupture. Now for shear rupture, the formula is different. We have a 0.6 here. Why do you have a 0.6? For any shear case in AISC, you'll find this factor 0.6 wherever there is shear stress, because this is the failure criteria for, if we consider when we have shear stress. If we have only the axial stress, That's one dimensional case. Then we can calculate the yield stress, right? Because we pull a rod and find out the yield stress. This is one dimensional. But when there is shear, there is axial force, three-dimensional arrangement of stresses, then we cannot define yield stress like the way we define stress in the stress-strain relationship of one-dimensional case. In three-dimensional cases, we talk about von Mises failure criteria, von Mises stress. And if we have only pure shear in three-dimensional way, pure shear, then the stress that we can compare with yield stress, von Mises stress, that will be 0.6 of FU. So from there, we get this 0.6. Now, that was all about design for tension. Now, if we talk about design for compression, then the limit for the slenderness is even less. You understand that if for compression, buckling is a major concern. So the scale by R ratio can never be more than 150. We have to keep it down to 150. And now you see there are some in the bottom. We calculate PN. There is nominal strength. We multiply a stress FCR, a critical stress. Since we talk about buckling, we talk about critical stress. Critical stress with gross cross-section, and we calculate the nominal strength. Now, this FCR, there are two different cases, and there are two different formula for FCR. In one, and they depend on the scalar ratio, slenderness ratio. There is one limit, 4.71 root over E by Fy. So depending on this limit, if it is less than the KL by R ratio, slenderness ratio is less than this limit, then the formula is this, and if it is more than this, then there is a different formula. Okay. Now, if it is more than 4.71, then this is basically like Fe multiplied by a factor. Now, what is Fe? Fe is nothing but the Euler buckling, critical Euler buckling load. Here, stress, critical Euler buckling stress. So now these are just like formula. You have to get these values of the stresses and put them in the formula and get FCR, and then you will get PN. That's so boring, but there's some interesting stuff in it actually. If we see some graphs, that makes it a little bit more interesting. The thing is that this limit 4.71 root over E by Fy, that is a limit beyond which we call a column or a member long, as if long column, and if the slenderness ratio is less than this, then we can think of the member as like a short column. So when the slenderness ratio exceeds this limit, we can be very sure that there will be buckling before anything else. There will be elastic buckling, that long before it reaches the yield stress, the stresses reaches yield stress, the member will buckle. This is member buckling, not local buckling. The whole member will buckle. So due to compression, if the slenderness ratio is high, then we'll find buckling first. So then the capacity will be dictated, will be governed by buckling. So this is depending on the KL by R ratio, the longer the member, the less stress it can endure before buckling. So the curve goes down at the right side of the red line, like this, like parabola, second order curve, like a parabola. So that is the for long columns, and for short column, two things may happen. Actually, in the finally, if it is very short, then the whole cross section will yield first, not buckle. So near this vertical axis in near these places when the capacity will be almost like Fy, that is yield stress. That is all the points, all the fibers of the section will experience yielding before it fails. So that is a very good case. So we can use up all the material up to its yield stress. So this is the maximum capacity one section can have, and that is called plastic capacity. In terms of moment, we call it plastic moment MP. In terms of load also, you can call it, that is completely plastic. The whole section becomes plastic. So this is the case, and in between these two, that is elastic buckling and plastic case, there will be a transition, and that transition is shown with this complicated equation 0.658 Fy by Fe multiplied by Fy. This is just nothing but a curve fitting exercise kind of. So this curve, the formula is complicated for that one. This actually refers to the inelastic buckling, that some part of the section will go beyond elastic limit, and in the inelastic stage there will be buckling. So this is in elastic buckling stage that may happen for short columns. So this F here refers to that stage. So that's why we have two distinct formula. One, when the KL by R ratio is very big, elastic buckling. If we want to allow that, okay, very good, no problem, but the capacity will be very small. And if the slenderness ratio is within this limit, 4.7 root over E by Fy, there will be inelastic buckling. And if our member is very short, then there may be complete plastic capacity. So that is the concept. Now, as I was mentioning, there actually buckling may be introduced by not only compression, buckling may be induced by flexure, because for flexure there will be compressive stresses, and the compressive stresses may induce buckling. For torsion, you may be surprised that torsion causes shear, right? But due to torsion, there may be other types of stresses too, depending on the cross section, shape of the cross section. There may be warping stresses, which are normal stresses, and that may cause buckling. And there may be flexural torsional buckling, that is, due to the combined application of flexure and torsion, there may be buckling. Let's read a little bit. Flexural buckling. This type of buckling can occur in any compression member that experiences a deflection, right? You don't have to apply moment for these. For compression, when it buckles, it causes, it introduces flexural moment and flexural stresses. So in any compression member that experiences a deflection caused by, bending or flexure, if we apply flexure, okay, flexural buckling occurs about the axis with the largest slenderness ratio and the smallest radius of gyration, that is the weak axis. In the direction of the weak axis, there will be buckling. We know that once buckling is, buckling always occurs in the weak axis. Torsional buckling, this type of buckling only occurs in compression members that are doubly symmetric and have very slender cross-sectional elements. These, we're talking about elements, right? Not members. That is either flanges or webs. It is caused by a turning about the longitudinal axis. Torsional buckling occurs mostly in built-up sections and almost never in rolled sections. Rolled compact sections, we seldom, we do not expect torsional buckling. In cases of built-up sections and non-compact section, we can expect torsional buckling. Flexural torsional buckling, this type of buckling only occurs in compression members that have unsymmetric cross-section with one axis of symmetry. So in that case, flexural torsional buckling is the simultaneous bending and twisting of a member. This mostly occurs in channels, structural T's, double angle shapes, and equal angle, single angles. Sorry. So flexural buckling is the usual type of buckling that we define buckling as buckling, and torsional buckling when a member doesn't only buckle it at the same time. So no, that is flexural torsional. Torsional buckling is due to the torsion that causes buckling. We'll see that. And flexural torsion is it doesn't only bend at the same time it twists. That is flexural torsional buckling. Now torsional. Now, in case of not unsymmetric members, that is, if a member has like not two axes, the member those don't have two axes of symmetry, there we can expect flexural torsional buckling, right? But there may be two cases, even in that case too. One is the members may have slender elements, that is B by T ratio or H by TW ratio more than lambda R, or they may not have slender elements. That is the B by T ratio, H by TW ratio may be less than lambda R. It doesn't mean that the member will be compact, the section will be compact. No. To have a compact section, the slenderness, the width thickness ratios must be less than lambda P. And if the width thickness ratios are less than lambda R, we call them non-compact section, but not slender elements. Okay, so we have complicated looking formulas for that. So as you see that FCR for normal flexural buckling that I have shown in the graph. So these are the formulas for FCR for long columns and for short columns. But once torsion or flexural torsion buckling is possible, that there is lack of symmetry. So here you see that there are two, we are talking about two axes, FCR-Y and FCR-Z. And in the previous case, in these formulas, so here we are talking about R, radius of gyration. So that radius of gyration is in the weak axis always. But here we have two. One is FCR-Y, that is Y is always the weak axis. X is always the strong axis of, by definition. X is the strong axis and Y is the weak axis, and Z is the longitudinal axis. So there will be some issues of capacity in about moment along Z-axis, about Z-axis. So FCR-Z, this component comes from that. So, and you see FCR-Y will have to calculate just like the previous case, like the previous formulas, but FCR-Z, for that, the formula is completely different because this is related to shear. That's why we have shear modulus here. And polar shear modulus. Right? GJ is the shear rigidity. For flexural torsional buckling, the formulas become more complicated. Okay. Then we have both IX, IY, all the parameters. For doubly symmetric, we don't have torsional term. We don't have Z terms here. But we have some warping constant here. CW is warping constant. For singly symmetric ones, we have this FZ. Okay. And in completely unsymmetric case, so we have everything. So the formulas, they look complicated. Actually, now all the designs are automated. The software part is supposed to deal with this, but you have to have the understanding. When we have slender elements, then This formulas are, sorry, the formulas are rather simple. It looks just like the previous case, but there is only one term added, that is Q. Here you see Q, and this Q term is multiplied with Fy. This Q term, it depends. The value depends on if the element is stiffened element or unstiffened element. For slender, you understand? We are talking about slender elements. So when there are slender elements, and the question is, the slender elements are stiffened or unstiffened, or there are different formulas for this value of Q. So it reduces the stress, but the amount of reduction depends on if it is stiffened or unstiffened. And basically it depends on B by T and H by TW ratios. So, so far we have talked only about design for tension, design for compression, now design for flexure. Design for flexure, we have to understand for flexure the limit states, that is how we are expecting the sections to fail. Will it yield? Will it buckle? In what type of buckling will be there? You see at the bottom there is a long table like this. The number of table is 6, 10, 3. For example, for this I section or channel section, if flange and web everything is compact, then we can expect two types of limit states. One is Y, yielding, and another is LTB, lateral torsional buckling. We'll see what is lateral torsional buckling. But for another case, if there is a non-compact flange in I section, we cannot expect yielding. Yielding is very good. Yielding means that you are completely using the section. All the fibers are reaching yield stress. That's fantastic. That is, you're getting very high capacity. But when we don't expect yielding, that we know that it will buckle for non-compact flange section. So not slender, non-compact or slender. Sorry, non-compact or slender. In that case, we can expect lateral torsional buckling or flange local buckling. You understand? The flange is non-compact or slender, so you can expect flange local buckling or lateral torsional buckling. So this is a list. So from this list, we can identify which checks we are supposed to give to calculate the capacity. So depending on that, there is no meaning in this type of I section where the flange is slender or non-compact to check for yield. We can easily do that, but there is no meaning. We will always get higher capacity, which will not cover. So like that. So from this table, it gives an indication that which checks we should give to calculate the capacity. Now the limit states are the different figures. Like here you see that on the top left, that is lateral torsional buckling. As during buckle, it twists sidewise. This is lateral torsional buckling. On the right side at the top, you can see the flange has locally buckled, bottom flange. On the left side at the bottom, you see that the web has buckled, web buckling. And at the bottom right corner, you see that the flange, tension flange has yielded at the bottom. So for different reasons, this can happen. So there are some, these are some pictures of different types of limit states. But ultimately, the same story. There will be 3 stages, depending on the slender width thickness ratio, that is element slenderness ratio. Depending on the ratio, when we calculate capacity, there may be 3 stages. If the width thickness ratio is more than lambda r, That means we are talking here, we are talking about flanges. That's why they're F's. So if the slenderness ratio is more than lambda r, then that will be slender element. So we'll expect elastic buckling. That is, the no fiber of this flange will reach elastic sigma y yield stress. It will buckle. If the slenderness ratio is in between lambda p and lambda r, then we'll have non-compact flange. What we can expect is that there will be inelastic buckling. So there will be some fibers where they will reach sigma y, but it will ultimately buckle. In the compact flange, when slenderness ratio is less than lambda p, we can expect almost plastic limit state, that is MP, plastic moment, that all the fibers will reach sigma y. So you'll have very high capacity. So we'll have different formulas for 3 different stages. And for flexural calculation, we'll have phi B 0.9 and omega B 1.67 always. So there will be some safety factors, some capacity reduction factors. That's phi B. Anyway, so depending on these limits, we'll have different formula. Now we have to think of another thing, that what would be the moment rotation or moment deflection scenario for different. We talked about elements. Now we're talking about the whole section. In some cases, we can reach complete plastic stage, so we'll have a large ductility and high moment capacity. In some cases, we'll have inelastic buckling. In that case, the ductility will be less, that is, deformation capacity or rotation capacity will be less, but we may have reasonably high capacity in terms of moment or strength. And when we'll have elastic buckling, then the capacity will be very low and the ductilities will also be low. These are the scenarios we have. Now, lateral torsional buckling. In lateral torsional buckling, actually, in case of pure torsion, what we have the cross sections that rotate. A cross section rotates with respect to another cross section. In case of lateral torsional buckling, they will be along the length, they will be bending and lateral torsion together. I think I have another picture for that. I forgot to add. Anyway, tomorrow I'll show the picture for lateral torsion buckling. And because torsion is involved, that's why we have shear stresses. That's why we have shear rigidity Gj here. That is shear modulus of elasticity and polar moment of inertia. And this type of torsion always, in the I section, always causes warping. That is longitudinal stresses to normal stresses too. So there's those normal stresses that the warping constant that reduces the capacity. So CW is another warping constant that comes into play. So ultimately, the capacity is expressed in this type of formula. So there may be 2 cases. One is beam supported all throughout. There is no so this explanation that I explained and the formula related to these are for beam supported all throughout. So there will be no lateral torsional buckling. So in case of unsupported beams, when there will be lateral torsional buckling, still these 3 phases are possible. But in that case, whether there will be lateral torsional buckling or not, that will depend on unsupported length. So here we are not talking about lambda, that is stiffness, slenderness ratio or width thickness ratio of different elements. We are talking about unsupported length. So we are talking about L. So similarly, we'll have LP and LR. If LR is so long that there will be inelastic buckling before reaching yield stresses, if the member experiences lateral torsional buckling, then that is elastic buckling. The capacity will be very low. In case of inelastic buckling, when some portion of the members will reach inelasticity, yield stress, and then buckles, so that is the second phase. And if the length is so short that it doesn't buckle, it yields first, then that is the case. And now the line shown at the bottom, that is the basic formula, but that formula is derived for cases like when the moments are equal on both two sides of a member. But when the moments are, the maximum moment is m, and we are calculating everything for m, and the other side we have less moment, then we can increase the capacity a little bit, and this factor is called CB, due to uneven moment on both two sides. So if this is uniform on both two sides, then CB is 1. But if it is not uniform, then we can increase the capacity a little bit. So these are the formulas. So we have this MCR, which is this is the formula for lateral torsional buckling that I've shown earlier, and then this is the this is MP, that is plastic moment. That is, we can multiply plastic section modulus with yield stress, and we can get MP. And in between these two, plastic moment capacity and this elastic buckling, lateral torsional buckling moment capacity, we can just linearly interpolate. And this is the formula shown at the top is nothing but a linear interpolation between these 2 points. So, and if we want to keep the unraised length, unsupported length within limits to avoid elastic lateral torsional buckling, so we will these limits LP and LR will guide us that what should be the unbraced length. So we can identify where we have to put bracing to brace sections. No, now I think, am I right? So it's 9:30. I'm supposed to give lecture until 9:30, right? Dr. Prabhu, I'm there. I've already.
Professor Raquib, it's till 10 o'clock.
So it's already over, right? So I was very slow today. So I can go for question answer session. I'll take some questions, not many, because I have already passed the 9:30.
Professor Raquib, typically go up to 15 minutes before closing.
So can I cover more material, or should I go for questions?
Yeah, you're supposed to be till 10 o'clock your time.
I see. Okay, then it's okay. Thank you.
Yeah, no problem.
Okay, so now I have to cover these parts, the basic parts, because tomorrow I have many other advanced topics that I have to cover. So design for shear. So we talked about tension. Remember, in tension we talked about what? Shear lag factor. It's interesting. Still is interesting. We design for tension. We talk about shear lag factor. We design for compression. We talk about flexural buckling. Now, again, we design for shear, and still we talk about buckling again. We know that compression causes buckling. So basically, this is not so difficult. We understand very well when you see this picture that here you see that there is a beam with stiffeners, and a very thin web. Now, if this beam that is applied with a vertical load, lateral load, transverse to the longitudinal direction of the beam, so that causes shear. So it's kind of panel shear we can see in between the stiffeners. Now, in between the stiffeners, there will be shear, and we know that the shear causes diagonal tension. Even in concrete, we know that shear causes diagonal tension. So diagonal tension is caused, and in concrete, we are always worried about tension. And in steel, we are mostly very much concerned about compression, because concrete cannot take tension, and in steel, compression causes buckling. So due to shear, panel shear, there will be diagonal compression, and due to that diagonal compression, there will be buckling. This is shear buckling. And there again, we have some. Here you see, to calculate the shear capacity, we have, what do we have? A 0.6, as I've said. In AIC, whenever you talk about shear, you'll always find this factor 0.6, because this is related to von Mises stresses of pure shear case. That is the yielding criteria of pure shear case in von Mises failure criteria. So 0.6 is there, and then we have 0.6 Fy is actually the yield case, yield stress for shear. And then you have web area, and there you have, this is wrong. This is wrong even in the code in BNBC. It is shown CW. It should have been CV, right? Because later CV is mentioned everywhere. It is actually, it should have been CV. So this, we apply one factor. That factor actually means that what percentage of this yield force, at what percentage of this yield force the member will buckle. So that is actually CV for shear. And there is again limiting slenderness ratio, H/2W, in this case 2.24. Beyond this, we'll have like long column effect, that there will be elastic buckling. Within this limit, there will be inelastic buckling. Okay. So when this is within this limit, so the phi factors and omega factors are mentioned here, and CV is 1, because we'll have we won't have elastic buckling. This is for rolled eye shape. For other kinds of shapes, this limit is different. This is 1.1. And for different slenderness ratios, the CV, we have to calculate CV, depending on the H/TW ratio, that what percent, because there will be buckling, inelastic buckling and elastic buckling. So depending on the H/TW ratio, slenderness ratio, at what point of that curve will be, so the capacity will have to be calculated accordingly. So the CV ratio depends on H/TW. Now, as you see that, suppose if we didn't have the stiffeners, then it would buckle much earlier. And if we have more stiffeners, that is, if we divide the panels in very short spans of panels, then the buckling will be induced later. That is, it can take much load before it buckles. Now, so that is the purpose of transverse stiffness along the web. So in the BNBC, there are some requirements for transverse stiffness. If our beam section is such that H/TW ratio, the web slenderness ratio, that is width thickness ratio, is less than this limiting factor, then we don't need actually transverse stiffness, but we have to give transverse stiffness at the end panels. That is when there is supposed to be concentrated loads, like at the supports or the points where concentrated load will come onto a beam. We have to give transverse stiffness. Otherwise, to restrict shear buckling, we don't have to use transverse stiffness if the H/TW ratio is less than this limiting factor. And to calculate and when we need, the moment of inertia should be, in other words, we can, using this formula, the second one, the second bullet point, we can calculate the spacing required for the transverse stiffness. So this is related to the spacing. A is the spacing between the stiffeners, TW is the web thickness, and J is defined like this: the spacing between the stiffeners divided by the height of the web. So this is related to that. So moment of inertia of the stiffener must be larger than this value. So if we have a particular plate having a particular amount of inertia, we can calculate A. Or if we first decide A, then we can design the stiffener. There's some details for transverse stiffeners, like we don't need to extend the stiffener to the tension flange at the bottom, but it has to be connected with the compression flange. Here is shown at the top. And secondly, there usually it is intermittent welding is used, and the welding is discontinued before reaching the bottom weld between the web and the flange, and the gap is usually from 4 thickness of the web, 4 times the thickness of the web, or 6 times the thickness of the web, something in between this. The intermittent welding is stopped before reaching the toe of the weld between the web and the flange, tension flange. So these are some details. There are some more details. Please consult the code when you design the transverse stiffeners. Now, as I've said, this is the same story. These are the limiting slenderness, web slenderness ratios, which define whether we'll have elastic bending, in that case the CV. The formulas look a little bit different, but the concept is same. CV is the C is 1 at the top, you see. So when C is equal to 1, that means you get the complete plastic capacity. And the other C's are reduction factors. What percentage of the plastic capacity you reach. So when it is elastic at the extreme right side, so C will be reduced drastically depending on the slenderness ratio. In between there is a straight line. Remember, in the case of flexure, we found that in elastic we don't actually have very rigorous formulation for this. What we do linear interpolation of inelastic buckling region. So in elastic buckling region between these two limiting slenderness limits, there will be inelastic buckling, and the formula for that region, formula for capacity, we actually just linearly interpolate depending on the slenderness ratio. So that's the idea. Now, one more interesting thing. This is so interesting. When we talk about tension, we talk about shear lag factor. When we talk about compression, we talk about flexural buckling. When we talk about shear, tension flexion, this is the peculiarity of steel structures design. So what is tension field action? Tension field, as I said, in case of concrete, when you talk about shear, we are always very worried about diagonal tension, right? Because concrete cannot take tension. In case of steel, we are worried about diagonal compression that causes buckling. But when there is diagonal compression, there is also diagonal tension on the other side. And when it buckles at one direction, there is compression. In the other direction, there is tension. But steel can take tension. So even after buckling, through the tension action that will act like a bracing, that will still continue to take load, because this part, as you can see, shown in the middle diagonally, in the left side in a test sample, this is buckled, but in the middle there is there you can clearly see something like a bracing. So that will still act like a bracing. So that will still take force, and that is called tension field action. So if we calculate the capacity only on the basis of buckling due to compression, diagonal compression, we will underestimate the capacity. So we can consider this tension field action, and that will give us more accurate estimation of the capacity. Now, when we can consider this tension field action for unstiffened here, this is not about element. We're not talking about unstiffened and stiffened element. We are talking about unstiffened beam and stiffened beam. That is whether there is transverse stiffener or not. For unstiffened beam, that is when there is no transverse stiffener, we can forget about tension field action. We cannot take advantage of that. If we have stiffeners, only in that case, but at the end panel, that is the panel near the support or near some concentrated load, in the end panels we cannot consider tension field action, because in those parts the shear is so high that the tension field action we cannot rely on that. Only in the interior panels we can consider tension field action, provided the slenderness ratio, there is a limiting factor kind of slenderness ratio, if that is within some limit. If the web is too thin compared to the flange, we cannot consider tension field action. So if this factor is satisfied, then we can consider the tension field action. Now in BNBC, the requirements are like that. We cannot consider tension field action for unstiffened case. We cannot consider tension field action for end panels. And this is the limiting factor. If the A by H exceeds 3, that is the spacing of stiffeners is 3 times the height of the web, then we cannot take that tension field action into account. And if the if the slenderness ratio or width thickness ratio of the web is high, then we cannot take that into account. And if the relative area of web, in other words, the relative rigidity of web and flange is high, then we cannot take tension field action into account. Similarly, there is some other other ratios like web height versus flange width, etc., etc. So if all these ratios satisfy, then we can consider tension field action in calculating the capacity. So the capacity is like this. If the H by TW ratio is very small, then you can take the complete plastic case, that is all the fibers will yield. So that is the maximum. If the H by TW ratio is higher than that, if in case of inelastic buckling, then we have this CV will reduce the capacity, and this right side, this one, which is related to A by H ratio, depends on the spacing of the transverse stiffness. This is the due to the tension field action. Vn is equal to 0.6 FYAW, that is the plastic capacity. We multiply this with CV, that is because of inelastic buckling, there will be some reduction. And the right side, plus 1 minus CV, etc., which depends on A by H, that is due to tension field action. Requirements for transverse stiffeners. So there's some other ratios and expressions which we'll have to check to find out if the transverse stiffeners are required or not, etc. Then we have, I think, covered the basic things: design for tension, design for compression, design for shear, and then there's some other topics like design for. Oh, I forgot to tell you that I have skipped some sections in the code which are related to design for flexure. For example, this part. Here I have mentioned only, or design for compression too, I have mentioned only these formula which are applicable to only for say double symmetric I sections or something like that. So there are other formulas for other types of sections. So the concept is same, just the expressions are different. That's why I didn't mention them here, but please check them in the code. You'll find different expressions for different types of sections. And now, when there will be a combination or torsion, things like that. So, for example, for combined flexure and axial force, so this is something basic in RCC. Also, you have this type of expressions. So you have to actually check when there is combined flexure and axial force. So there are some expressions for doubly and singly symmetric members. Here, one criteria is that for compression flange, the moment of inertia about weak axis divided by the moment of inertia about weak axis of the whole member should be in between 10% to 90%, which is usually the case. So there is, it always satisfies most of the time. So there, if it satisfies, then if the required capacity, if the required strength is only 20% of the available capacity, no, is beyond that, more than 20%, then we have this expression which has got a factor 8 by 9, and then if it is only 20%, then the expression is a little bit different. So in the case of which is only less than 20% the required strength, then we increases the requirement for axial force, like that. Now, design for torsion. So for torsion also the phi t and omega t are similar. There is one difference with tension. Remember, in tension we have phi t, that t is small t, and for torsion the t is capital T. In notation this is a difference, and even in tension, in some cases for rupture, we have the values of phi t as below as 0.75, but in torsion this is 0.9. In most of the cases, phi t is 0.9 and OMGAT is 1.67. Now, torsional capacity is simply the FCR, that is elastic buckling capacity, critical capacity multiplied by torsion factor, C. So it reduces this FCR by an amount, which is C. Now, there are expressions for round. Remember, we usually, when we expect torsion, we usually use HSS, that is box section, hollow structural sections, HSS. And for HSS, there's some formula given. And for round HSS and for rectangular HSS, we have different formula. For round HSS, we have two criteria, and we have to see which one is larger. And for rectangular HSS, it depends on the web slenderness ratio, width thickness ratio. Anyway, again, we can understand that we have one elastic, completely plastic case, in elastic buckling and elastic buckling phase. Similar in all the mode of load transfer. When there is combined torsion and shear and axial and flexure, then we have to give this check. So for HSS members and for non-HSS members, we have different sets of formula. So you have the basic concept is I have already discussed, so I'm not going into the detail of these things. So that's it. That's it. So the basic concepts I have covered today regarding what type of analysis we have to conduct, and in the design phase for tension, compression, shear, and torsion, what are the considerations that we have to make, and what is the basic concept for all these for steel. So there are some peculiar things that we have to consider, which is completely different from RCC, concrete, like tension, field action, things like that. And buckling is always the governing criteria in designing. So that's it. Now the questions. Right. So the first two questions I have already seen before starting this lecture today. So I'll discuss about these tomorrow. The first two questions. So I'll discuss about them tomorrow. Now the third one is I can put down what. Oh, okay. The third one, AC702 or AC705 allows the use of steel OMF with some height and dead load limitations for structures assigned to seismic design category D and E. BNBC table 6 to 19 does not provide any guidance on this. Actually, AISC 316.05 that does not allow. So BNBC adopted this table from AISC 316.05. So according to that, the SDC D is not allowed. Oh, I see. Sorry, this is for loading, right? Loading, I have to check. AC705, does it allow ordinary? Yeah, ordinary moment. I have to check it out. Sorry, I'm wrong. This is not from AIC. This is from AC705. What is not allowed is that without OMRF is allowed probably. For steel, OMF is allowed. I have to check. But with seismic provisions, there are some seismic provisions even for ordinary moment frame for steel. But those without any seismic detailing, that is not allowed for seismic design category D. But I'll check. I don't have it. I don't remember it right now. Is it a prerequisite for moment connection to place bolt outside flange? Outside of flange? No, no. That can be welded. Flange can be welded. This is not a prerequisite always for moment connection. Is it a prerequisite for tomorrow? We'll discuss about connections too. Is it a prerequisite of moment connection to place the same question on column-based connection to connect column beam flange to column flange? If bolt is inside flange in base place connection, and if beam flange aren't connected to it column flange, then is it possible to consider partial fixity? It is possible to consider partial fixity. It is possible to consider partial fixity, but not fully restrained FR. What is the allowable sway shed structure? Did you mean that allowable sway for shed structure? So those limits are given in the loading chapter, and those limits are given in the loading chapter depending on wind load. For wind load we have one limit, and for seismic ones, depending on the value of R, we have different drift limits. So addition to that, I'll check. Shed structures. What do you mean by shed structures? Do you mean gable frame? Whatever, we have the same sway criteria. In SDCD, SMRF is a requirement for not always. SDCD doesn't mean SMRF always. But for single-story long-span steel shed in SDCD, is quite uneconomic to design SMRF with compact section. Do you have any suggestion regarding this? Tomorrow we'll talk about this, but in SDCD, SMRF is not all. This is, we can have other systems than SMRF in SDCD. Sound is too low, sorry for that. Is there any limitation to flange thickness and web thickness ratio? Yes, of course. Depending on that, the tension field action, for example, depends on that. So depending on the flange thickness to web thickness ratio, the amount of tension field action and the design of transverse stiffener is also depends on that. To design a fixed connection for base plate, is it necessary to check rotation? To design fixed connection for base, is it necessary to check rotation against the moment if there are no bolt outer side of column? For base plate connection, you have to place bolts outside the column to make it fixed. Or you can have a simple that is hinge. You have to assume that as hinge connection. Nonlinear analysis is required for partially moment connection. Can you explain this? Yes, I can explain this. So in our linear analysis, what we consider is that there is no relative rotation between beam and column. So if the column rotates by an angle of theta, beam also rotates by an angle theta, right? So you have so you have complete rigidity between these two angles. But when you have partial rigidity, as if you have a rotational spring in between beam and column. So the transfer of moment and the rotation, they are related, they are interdependent. So you have, so in linear analysis, what you can do, depending on the load, you can definitely calculate the deformation, right? But when we have this scenario that you have a rotational spring inside, the amount of moment actually at the joint changes depending on the rotation. So this is an iterative process that causes nonlinearity in the analysis. So that is in the equation. In the equation, there are parameters that becomes function of the response. That gives nonlinearity in the equations. If all the truss connections are designed for fixed and moment connection, we will allow to assign effective factor 0.9 for vertical truss members. Effective factor 0.9. 0.65 for top and bottom chord. If it is completely braced, yes. If it is completely braced, that depends on sway. So for truss, vertical truss that is completely braced, right? In that case, you can assume. But for frames, a vertical frame which is not braced, then you have sway. Then K will be more than 1. If all the truss connections are designed for fixed, same question, is there any relation between web thickness to flange thickness? I have already answered that. What is the limit for sway of steel shed based on BNBC 2020? I don't, first of all, this term steel shed is not used in the code as it is. And secondly, there is no specific limit of sway unit specifically defined for steel sheds. As we know that bracing is a tension member. Bracing is a tension member. You can design bracing as tension only member, but bracing doesn't have to be a tension member. It can be a compression member too. Can we analyze heavy bracing made with a size 100 box as tension only? In your analysis, you want to assume that as tension only, right? You want to ignore the compression that it can provide. So in the analysis, you are ignoring the compressive forces that will come from this bracing. I don't think this is wise. I don't think this is wise because it will be on other members of your structure. So this will not be wise to consider in the analysis this as tension only. What is the allowable limit of lateral displacement, wind or earthquake for singles? Same question. I will check this. As far as I know, there is no specific allowable limit for sway for steel sheds only. For non-compact and slender members, can we control the buckling of a steel structural member? For non-compact and slender members, can we control the buckling of a steel structural member through providing stiffener in a potential location by analysis throughout the length? No. Stiffeners, by stiffeners, you can restrict shear buckling, but local buckling For local buckling, it depends. For example, for local buckling of flange, it depends on the B/T ratio of the flange. So by providing stiffener, you cannot change that. There will be places where the B/T ratio will still be quite high. So buckling will occur in those places. So just by providing stiffeners, you cannot restrict all kinds of buckling. Is there any requirement to check steel beam rafter deflection against lateral load? Separate deflection limit for beam or rafter? Probably not. I have to check. So I'll check all these deflection related questions. So where am I? As we know that bracing is the tension member, can we, the same question, what is the allowable limit for same question for non-compressed liner? Okay. Is there any, dear sir, for tension member L/R ratio 300 in our BNBC 2020, but AIS 705 explain for tension member L/R ratio 300 recommendation not triggered AISC design 14 example D2. So sir, okay. Even yes, there are clauses that says that we can go for higher slenderness ratio, but we have to ensure the performance. There is a clause like that. I suppose in BNBC too, this clause is there. So, sir, which will follow for angle or pipe section tension member? It is always better to be within this L/R ratio, 300, but we can go beyond that. There is a clause, but we have to justify that through analysis. So 300 is the limit, but beyond that, we have to justify the use. So I'll check the clause, and tomorrow I'll try to answer this. What is the exact clause related to that? So there may be many more questions. How many? Not many. So I'll try to finish. Dear sir, Assalamu alaikum. For non-compact and slender members, can you control buckling for a steel structure? No, I have answered. Stiffener, no, I have answered this. Dear sir, nowadays regarding fire rated requirements, it is better to go on steel structures than RCC. Is it better? So tomorrow I'll try to cover this part 2. There are provisions for fire. So this is not a simple answer that RCC just, for example, in many industrial buildings, steel construction is still a better choice. For example, for low height, 1-story to 2-story, for those types of structures, even for fire, that doesn't pose much risk. So this is not a simple answer. It depends on the number of stories, the kind of use, and what type of preventive measure you are taking against fire. So all these things you have to take into account before taking any decision. All examples for iJoist and similar members. What about truss member? What do you mean by angle? Truss member, you mean angle or channel sections? There are formulas for angle and channel sections too. So I just gave examples of I sections, but in the code you'll find all the relevant formulas for angle sections and channel sections. What we would consider lateral restraint of an I section? Okay. When the top flange is restrained, when both flanges are restrained, then when the web is restrained. When only the top flange is restrained and bottom flange is not restrained, that is not fully restrained. When both flanges are restrained, that is fully restrained. When the web is only restrained, that is a simple shear connection. What is the advantage of direct analysis method over effective length method? Effective length method basically is an approximate method. Direct analysis method is also an approximate method, but more sophisticated, that can take into, tomorrow we'll discuss this, that can take into account all the four stability factors. It considers all of them in a systematic manner in direct analysis method. What do you consider laterally restrained for an isolation? Same question. Which method is economical for steel structure design, LRFD or ASD? I don't think in the present design method, LRFD and ASD, that makes much of a difference. But LRFD is currently LRFD is more often used than ASD. Is it required to check the slenderness of the beam for compression and comply KL by R should be less than 150 for compression, not 200. This is according to AIAC 360. So it will be very helpful for us if we discuss the fire requirement. Okay, tomorrow I'll try to cover. So thank you so much. This is the first time I could finish answering all the questions. So if you have more questions, then probably you can drop them right now here, and we'll answer them later. Thank you so much for participating in the webinar. Tomorrow, hopefully we'll meet again. Thank you.